Section 4.2 is on function notation, which we discussed yesterday in day 1 and watched the video. So today is kind of a wrap-up of this new concept of a function and the notation for it. Okay, so a relation versus a function. A relation is a relationship between any two variables, any kind of relationship. But a function is a special kind of relation. It's more specific. And the definition is for a function, for every input, there's only one output. So x values cannot repeat. So anything you put in, only one answer can come out, not two answers or the same answer. Or not two different answers, I should say. And all functions are relations. All relations are not functions. So what does that mean? It just means that we could draw a Venn diagram, so it makes more sense. If we had a Venn diagram of this last statement, we have our broader term of a relation. So I'll do it right here. All right, so here's a relation. Everything in here is a relation, a relationship between two variables. Functions are a subset of that. So all functions are relations, but not all relations are functions. That's what that means. Okay, so let's take a look at graphing. It passes something called the vertical line test. So if you drop a vertical line on any graph, it should only touch the graph once. And if it does, it's a function. And the reason is, for every x value, so here's the x value, here's that x value, it should only have, actually represents is at this x value, there are two answers, and that is not a function, because every input there should only be one answer, one y value. Okay, so it passes the vertical line test as if you draw a vertical line, and anywhere in your function, it should only meet that line once. If it meets it more than once anywhere in your graph, it's not a function. So that's the vertical line test. Okay, which of the following are functions? This first one's meant to be a table. So let me make it look more like a table here. So here are your x and your y values. Again, definition of a function. For every x value, there's only one y value. So if we take a look at these are all different x values except for 4. And right here, 4, anytime you see a 4 in this graph, it should only have one answer. It should only be 9 or it should only be 7. So this is not a function. Right here, if you want to make it into a table, you can. It might look something like this. X, Y. So when I plug in a -3, I get a 1. When I plug in a -5, I get a 1. When I plug in a 6, I get a -7. When I plug in a 10, I get a -7. And at first you might think this is not a function because of repeating y values, but that's okay. Every time I put in a -3, I should get a 1. Every time I put a -5 in, I should get a 1. And that's okay because for every x value there's a different, or there's the same y value. So as long as every time you put in a -3 you get a 1, or as long as every time you put in a 6 you get a -7, this is a function. So y values can repeat, just not for the same x value. So this is not a function because when I put in a 4 I got something different. This is a function because for every x value there's only one y value. Alright, graphs. Again, does it pass the vertical line test? If you drop a vertical line, is there only one answer? Right here along this value, which I didn't draw that line very well, but along this value right here, there's only, for this x value 1, there's only one answer. But if you drop a vertical line here, there's two answers for this x value, so this is not a function. Here you just have to make sure for every x value there's only one y value. Yep, it looks like this is a function because there's only one dot per x value. Here, when I plug in a 1, I get a 1. When I plug in a 2, I get a 3. When I plug in a 3, I get a 4. When I plug in a 4, I get a 2. This is a function. It would not be a function if I plugged in a 1 and got two different answers. That would not be a function. We talked about function notation. It's just replacing the y with an f of x, and that means it's a function. And then when you replace the value of x, it tells you what to plug in. So we practiced this yesterday. So let's say this is a function. It's a line with the y-intercept of 4 and a slope of -2. And anything linear will be a function. For every x value, there's only one y value. So they say f of x equals negative 2x plus 4. What does f of 1 mean to evaluate? It means to plug in a 1. So we have negative 2 times 1 plus 4. So we say f of 1 equals 2. For the next one, plug in a negative 3 for x. So we have negative 2 times negative 3 plus 4. And we would say f of negative 3 equals, this would be a 10. And f of 1/2 means you plug in a 1/2. Half of negative 2 is negative 1 plus 4. So we have f of 1/2 is 3. Okay, so there's examples of using function notation. There's one more type of problem. We can go back to this one, but here's the other type of problem. What if I don't tell you what to plug in for x, but I say solve for x? So if we use this same one right here, we have 8 equals x squared plus 4. This one we plug it in for g of x, not for x. So 8 equals x squared plus 4. Solve for x now. So solve for x. Subtract 4 from each side. So we get a 4 equals x squared. To get rid of a squared, you take the square root. We have x equals plus or minus 2, because 2 squared is 4 and negative 2 squared is 4. So that's solving for x. There's a difference. Here I'm telling you what to plug in for x. Here I'm saying, all right, your answer is this. Solve for x. So for this one, we'd plug in a negative 2 here. So we get 4 plus 4, which is 8. So g of negative 2 is 8. But here when you solve for x, you plug this in for g of x. So we put the 8 in right here and then solve. So there's a difference between the two types of problems. So here's the assignment. Again, a wrap-up of function notation. And again, this was a 2-day section, so if you struggled and you only watched this podcast, watch the first one as well.